Hello everyone, my name is Peter Hönig and I work at the Automation and Control Institute of the Technical University of Vienna. And I'm happy to welcome you to my talk about shape-biased texture-agnostic representations for improved textureless and metallic object detection and 6D pose estimation. So, let's get into it. A few words about the motivation behind this work. So what's our challenge? In our research group, we want to perform robotic grasping with the help of computer vision. And this involves the tasks of object detection and pose estimation. We want to tackle a broad range of objects, and this involves textureless and metallic objects as well. However, current methods struggle to recognize these object materials due to reflections or the lack of textural cues. We hypothesize that shape features are more effective for such materials, and that brings us to our goal: inducing a shape bias for texture-agnostic detection and pose estimation. So, what are the key contributions of our paper? First, the shape bias for textureless and metallic objects. We use UV mapping to introduce a shape bias which improves object classification and outperforms traditional style transfer. Then, there is the general applicability and improvements for detection and pose estimation. We show that our UV mapping approach is easily integrated into data rendering engines, and we show improvements across 5 detection and 2 pose estimation methods on the TLES and ITOT datasets. And we also show enhanced robustness with less reliance on online data augmentation and less resilience toward image perturbations. So, when we talk about inducing a shape bias, one has to note the previous work of Gairos et al., who showed improved classification after training a ResNet-50 network with a stylized version of ImageNet. However, this stylization does not preserve accurate object geometry, as it is shown by the example image on the right. Geometric consistency is, however, necessary for tasks where we do geometric reasoning, such as 6D pose estimation. We therefore present our method of inducing a shape bias via UV mapping. We call it texture randomization, and it is specifically designed for physically based rendering. Instead of using uniform color distributions to render textureless and metallic objects, as it is currently done by, for example, BlenderBrock, we download textures with various patterns from a Creative Commons database. We then perform the low-cost UV mapping. This step has negligible computational overhead in comparison to the uniform color distribution. And then we render the training data. So, how do we evaluate our method for inducing this shape bias? First, we want to directly compare to the shape induction via the style transfer and analyze the influence of texture randomization onto image classification. We then continue with an evaluation of 5 object detectors and 2 pose estimation models. All experiments are performed using the TLES and ITOT datasets. TLES features 30 textureless objects, some of them very similar, and ITOT features 28 metallic objects with dim lighting, so 2 datasets with very challenging object materials and conditions. So, let's talk about results, and first the image classification. In our experiment for image classification, we train a ResNet-50 model on the TLES dataset. We conduct experiments on TLES variants with the uniform color distribution, which will induce a texture bias. Then we will compare that to the induction of the shape bias with the stylization and the texture randomization. Now, please look at the table on the right bottom side. As it is shown in this table, our method of inducing a shape bias via texture randomization outperforms the shape bias via stylization and the texture bias via uniform color distribution. Based on the findings related to image classification, we continue with experiments on 5 object detectors, namely FasterRCNN, RetinaNet, YOLO-X, YOLO-V8 and YOLO-V10. For each of the detectors, we report the mean average precision of 2 cases. First, the default case, which means that the out-of-the-box data augmentation is used that is presented in the respective paper. Secondly, there is the tuned variant, which refers to optimized data augmentation for the shape bias induction. More information on the relationship between online data augmentation and texture randomization is given in the ablations. Now let's focus on the table. The table here shows that especially the newer YOLO detectors benefit from the induced shape bias. For faster RCNN and RetinaNet, the shape bias still boosts the performance when data augmentation is not handcrafted for specific datasets. Now let's look at the results for 6D pose estimation. 6D pose estimation is evaluated using Pix2Pose and GDRNet. We use the average recall as described in the BOP paper by Hodan et al. One can already see that the improvement is greater for the TLES dataset compared to the ITOT dataset, and that performance benefits most from a shape bias in both the detection and the pose estimation stage. To investigate our findings further, we conduct multiple ablation studies. We start with the ablation of the number of random textures to investigate the relation to object detection performance. Here we found out that with 5 random textures, we already reach more than 93% of the maximum accuracy that are achieved. When increasing this number to 100 random textures, we achieve 99% of the maximum accuracy for YOLO X. We continue with an ablation regarding online augmentation and its interaction with our texture randomization approach. To investigate this relation, we introduce a scaling factor to evaluate different probabilities of augmentation methods. Overall, we found out that object detection and pose estimation benefit from less data augmentation when texture randomization is applied to induce a shape bias. Around 20 to 40% of the original augmentation probability is suitable based on our results. Since the TLES dataset offers cut models and reconstructed meshes, we evaluate the relation between mesh origin and the type of bias. What we found out was that the cut models in combination with the shape bias induced by texture randomization yield the maximum results, while the reconstructed mesh with the texture bias yielded the worst results. Finally, we conducted an ablation to investigate the resilience of shape bias pose estimation methods toward image perturbations. We used GDRNet for these experiments on the TLES dataset. Here we discovered that the shape bias GDRNet is more resilient toward Gaussian noise, shot noise and brightness as compared to the baseline method. Alright, this brings us to the conclusion. In our paper, we show that inducing a shape bias via texture randomization improves classification, object detection, and pose estimation of textureless and metallic objects. We evaluate our approach on 5 object detectors and 2 pose estimators. During our ablations, we also show how a careful balance with data augmentation is necessary. Finally, we show how the shape bias leads to increased resilience toward image perturbations. Thank you for listening to my talk. At this point, I also want to thank the Austrian Science Fund and the European Commission for funding this research. And if you're interested in the paper or the code, feel free to visit our project page accessible via the QR code or just send me an email. Thank you.